I would like to express my sincere gratitude to the Pontifical Academy for Life for the kind invitation to the Third International Congress. I wish I could be there and have discussion, but unfortunately my schedule did not allow it. I deeply apologize for not being able to attend the Congress. In this video, I would like to introduce recent progress in iPSL research and application. Again, I'm Prof Yamanaka, Center for iPSL Research and Application of Kyoto University, Japan. We have been working on this new technology which we designated iPS cells, induced pluripotent stem cells. We developed this method 10 years ago in 2006 by introducing these 4 factors into mouse skin fibroblasts. We became able to convert skin fibroblasts into stem cells, which are very similar to, almost indistinguishable from embryonic stem cells. We designated these cells iPS cells. In the following year, 2007, we became able to recapitulate same iPS cell generation from human skin fibroblasts. This is a microscopic image of human iPS cells. They represent one of the smallest cells that exist in this world. However, their ability is tremendous. First of all, we can expand iPS cells almost infinitely. In addition, after expanding, we can convert iPS cells into virtually all types of cells that exist in a body, such as neurons, muscle cells, heart cells, and so on. Thanks to these 2 potentials of iPS cells, we have been trying to use iPS cells in helping patients. There are 2 major medical applications of iPS cells. In order to advance medical applications of iPS cells, Kyoto University launched a new research center in 2010, Center for iPS Cell Research and Application, CIRA. Our mission is very clear. Our mission is to contribute to new therapies using iPS cell technology. Among the 2 major applications of iPS cells, I would like to give you some examples of cell therapy first. Approximately 1.5 years ago, Dr. Masayo Takahashi of Kobe Riken Institute, her group operated the very first operation using human iPS cells to a patient suffering from age-related macular degeneration. Her team generated iPS cells from patients' own skin cells, then generated retinal cells from patients' own iPS cells. And they transplanted newly developed retinal cells back into patients' eyes. I heard from Dr. Masayo Takahashi that patient has been doing well. She is able to maintain her vision, whereas the other side, operated eye is getting worse and worse. This is another example of iPSL application in cell therapy. Professor Koji Eto of our institute, he can now generate functional blood cells, including platelets and red blood cells. He is now trying to use these cells in blood transfusion. Countries like Japan, who are facing rapid aging society, has a huge problem in blood transfusion, because we're going to have many more elderly people who needs blood transfusion, whereas we will have less and less young people who can donate their own blood to blood bank. So only 5 years or 10 years from now, we will be short on blood donor. So alternative approaches like this is very important. One of the biggest advantage of iPS cells is to use patients' own iPS cells. Namely, we can perform autologous iPS cell transplantation. And indeed, the very first case by Dr. Masayo Takahashi was an autologous iPS cell transplantation. However, we learned from the first case that autologous iPS cells have two major concerns about clinical application. First of all, they are too expensive, and also they take too long. It took us almost a year from isolating skin cells from patients to operation. And also it costed us approximately nearly $1 million to generate iPS cells and to perform rigorous quality control. So to bring this technology to thousands of patients, these two issues, time issue and money issue, can be a very high hurdle. In order to overcome these two practical problems, we have been working on iPS cell stock for regenerative medicine. In this strategy, we make iPS cells not from patients' own cells. Instead, we make iPS cells from healthy volunteers or from cord blood samples. We have already started this project. We collected blood from Japan Red Cross and also cord blood bank. We brought those blood cells into CIDR, where we have been generating clinical grade iPS cells in our cell processing facility. We have distributed the very first iPS cell stock line August in 2015. Let me briefly discuss about the other application of iPS cells, which is disease modeling and drug development. Dr. Noriyuki Tsumaki of our institute, he has been working on orthopedic application of iPS cells. He and his team generated iPS cells from patients suffering from achondroplasia. He generated iPS cells from patients and also from a normal, healthy, control individual. When iPS cells were undifferentiated, he did not see any obvious differences between patient and normal control. However, when he tried to induce cartilage tissue from iPS cells, he observed a huge marked difference. From normal iPS cells, he was able to induce beautiful cluster of cartilage tissue. In great contrast, from patient iPS cells, even with the very same procedure, he was not able to produce functional cartilage from patients' iPS cells. This means that he was able to recapturate disease phenotype in Petri dish, that is, not being able to generate cartilage. By utilizing this disease modeling in Petri dish, he has been testing many drug candidates, and he identified one existing drug, namely statin, is effective to recover disease phenotype in Petri dish. By adding this drug, even from patient iPS cells, he can now make functional cartilage. We are hoping that we can translate this finding in Petri dish with iPS cells into patients as quickly as possible. In our institute in Kyoto, more than 400 people, including scientists and staff members, have been working very hard to realize our mission. Our mission is to bring iPS cells to patients. We want to help patients suffering from intractable diseases by using iPS cells. We do hope that we can realize our mission in 10 years or 20 years. We will do our best. Thank you so much for your kind attention.